So Dr. Azizi is a medical doctor and clinical epidemiologist, currently working as a postdoctoral fellow at Stanford University, focusing on digital health, computer science, and artificial intelligence in medicine. Her research goals are integrating and practically applying computer science and AI methods in medicine to produce new knowledge and deepen understanding of health-related issues, ultimately aiming to improve patient care and decrease disease burden. So we are very happy to have you today, Dr. Azizi. And now feel free to take over and start your presentation.
Amazing. Thank you so much for introduction, and it's great to be here with you all. So I'm going to go over like classifications today, like give you an overall like concept of what it is, what are different types, and then we have some examples and codes in Google Colab that I think Sebastian will share with you. So we can go over them together and run the codes to and see how each model, like the most important models, work. So I think I cannot share my screen with you.
You should be able to now. And just for your information, participants, I'm going to share the link to the drive with all the PowerPoints and Google Colabs in the chat right now. Please, Dr. Azizi, go ahead.
Thank you. Okay, so let's start. So today we are going to first see what is machine learning. I think you've had this class before, so you all might know. And supervised versus unsupervised machine learning, and regression, classification, and different types of classification. And at the end, I'm going to also go over a bit of metrics that we use to assess these models, and finally, one example. So this is just my recommendation for everyone. If you are taking workshops and courses one after another and not doing a project, let's break this vicious cycle and let's start doing a project, because doing workshops and courses by itself is not going to teach you how to do AI or research or stats. And the way you learn is to start a project, learn the different models inside the project, learn from your errors. You're gonna have a lot of errors when you try different models, and that's how you can improve and progress and hopefully learn AI. So that's my 2 cents. And as a disclaimer, so this is mostly introduction to this subject, and I'm going from very basic to more detailed for broader audience. And I didn't include data cleaning methods. So one of the most important parts of doing a project, computer science project, is to first clean the data. And that's almost half of your work. So it's better to know how to do this. You should understand your data. You should know what's your outcome, what are your features, how they're related to each other, if you have any missingness or not, and then start your doing models and selecting models. If you, in the beginning, just download the CVS data and just run the model, it's not gonna work, and you're gonna work on that model like months and months, and you're not gonna get any results. So this is a very important part, and you have to know this before starting to do any of the models that I'm explaining. Okay, so let's start. What is machine learning? So there is difference between human and computers, and that is that human, they learn from experiences, but computers, they need to be told what to do, and they should follow the instructions. And so that's how we can get also computers to learn from experience too. If we give them data, we can teach them how to learn from their previous experiences, and that's how it's called machine learning. So the first topic in machine learning, I'm just going back to linear regression. I think you had this session previous week, but just a quick reminder of what is linear regression. Linear regression is actually, imagine that we want to find a line that fits best with these 3 points. The best line is really subjective. So we want the best line that has the minimum distance from each of these points. And so if we want to teach a computer how to do that, the computer really cannot eyeball it and say, okay, this is the best line. So the computer would draw random lines and see how the line fits best and try different multiple times to reduce the distance. And this is how we calculate the error of the model, the computer. So for example, now we start the line from here, and then we calculate the distance from the line in here and call it error. When we add all of these together, we see that, okay, now we have almost like somehow like a very big error. Then I move my line and I try a different line and see if the distance from the points and line decreases. When I add them together, I see that no, it increased. Then the next one and the next one and the next one. When I add, I see that this decreased and this is my best fit. And we repeat and repeat and repeat till we reach that minimum error. That would be this. So this is also called as gradient descent. So you imagine you are going down from a mountain, and you wanna where you are on the top of the mountain has the biggest error, and you want to reduce your error, and that would be very similar to the distance from the line that you see on the right. As you come down to the mountain, your error decreases. You can go on the to the left and increase the error, but it's best to come down and decrease it. And the best position is where you have the least error and you have the least distance. So that's why it's called gradient descent. And this is a very important terminology in machine learning, because that's for most of the models, that's our goal, to decrease this this error and to decrease gradient descent. So the line that I just told you was a very preliminary line. It's the linear line. It's the basic linear regression. But usually in real life, the relationships are not this basic. So you can have a relationship between lines that is like a circle like this, or you can have a relationship that is cubic polynomial and it's like this, like a curve. So machine learning algorithms will allow you to find these very complex and complicated relationship as well, not only a line. And that's the difference between machine learning and regular biostatistics. So today we are going to talk about classification. So we don't want to find the line that best fits one data, but we want to actually classify 2 types of data and see what's the best line that can classify these 2 types. So the first example, one of the very simple models in classification is naive bayes. So I just presented this with an example of detecting email spams. Imagine you have 100 emails and you want to detect the spams within your 100 emails. So you want to build actually a spam detection classifier. How would you do this? So first you look at your data, you see out of those 100 emails, you flag them, and you see 25 of them are spam and 75 of them are not spam. Now let's try to think of features of a spam emails may look like, and what are those features? So when I look at those emails, I see that the word cheap has been repeated in the most of the spam emails, and a few of non-spam emails. So let's analyze this and see if we can look for a word cheap in these 100 emails and see how many of these emails really contain this word. So this is the ratio. 20 of the spam emails and 5 of non-spam emails, they contain the word cheap. And so that would be about 80% to 20% split. So we can say the risk of having a spam is 80%, having a word cheap is 80% in a spam. And you can also present the 20% in non-spam as well. So from analyzing this data, you can conclude a rule. So the rule says if the email contains the word cheap, we are going to say the probability of being a spam is 80%, and that then it would then we can flag this in the future messages to see if we see a spam or not a spam. And we can repeat this with other words as well. So with the other words, for example, if we have a spelling mistakes, the probability of having a spelling mistakes in a spam is 70%. If they have missing titles, the probability is 95%, and etc. And then when you add them all together, then you can create this algorithm to be able to predict future spam emails. And that algorithm is known as a naive Bayes algorithm. So this algorithm has one assumption. The assumption is that the predictors shouldn't really correlate with each other. They should be independent from each other. And that's very hard. That's a very hard assumption, especially in real life and complex relationship. You cannot really find this type of predictors that really do not correlate with each other. But this algorithm has a good use as well. It has you can use it for text classification, for spam filtering, for sentiment analysis, and for your NLP model. That's it's really useful, and also for recommendation system and for real-time prediction, because it only wants to classify, and it's super fast, and it doesn't really consider the relationship between other predictors. So that would give you a really good classifier, a real-time classifier. So the pros and cons, as I mentioned, the pros is that it's really easy and fast, and it can run multi-class prediction models. And when the independence model holds, this actually is more powerful than the more complex machine learning models like logistic regression, decision trees. And but about the cons, there is this phenomenon called zero frequency. So one of the problem with this algorithm is that if one of your categories is zero in your training, then the probability of that category is going to be zero. And so it really cannot make a prediction in your test set because it was zero in training. You might have that in your test set. So that is called, it's a phenomenon called zero frequency. And to solve this, there is a smoothing technique. So you add similar number to all of your training and test, and then try that. So you won't have anything zero in your model, and you can try it. And it wouldn't affect your overall probability, but then the algorithm can run and continue the process. And as I mentioned, because assumption of independence predictors is not really applicable in real life, you cannot really use this in more complex machine learning, more complex projects and relationships. Any questions still here?
We have a question on the chat regarding, I think, the linear regression part. Can we determine the line of best fit by the correlation coefficient?
So the line of best fit by correlation coefficient is, so that would depend on, that's how we really do it in stats. With beta, we do that. And so that shows the relationship between each of these factors with each other. And then we have R squared, that's how we assess the error, and it shows the variability of each of these parameters inside the model. And that's how we assess the model in linear regression.
Thank you, Dr. Azizi. We have another question on the chat. This time is for what you were exactly talking about, so the zero frequency. Can we solve the zero frequency problem with just adding a 1 to each predictor?
Yeah, that's one of the models. And there's a simple smoothing technique. It's called Laplace estimation. So you can do that, and that would solve the problem. Yeah.
Thank you very much. I think that there is no more questions for now.
Amazing. Okay, so let's go to the next one. So now the most common famous classification algorithm is logistic regression. So in here, in opposed to linear regression, we want to actually separate these lines. We want to find a line that can best separate these 6 points, and to classify them. So how can we do this? So again, first we just draw a random line, and in this random line, we assess if it could classify or misclassify the dots, and we see that there is one error in here. There's actually 2 errors in here, and then we move the line. Again, we have 1 error, 1 misclassification. And finally, we find the best fit, the best algorithm that there is no misclassification, so there is no error. So this is actually, in reality, we use gradient descent also, but the error in here is called log loss function. And the idea is that it's a function that assigns a large value to the misclassified points and a small value to classified points. So that's the same concept with neural network. So in neural network is a part of deep learning, but we cannot really draw one line to actually divide, to classify these 2 types of dots. We can create a circle, or we can have 2 lines, one in each different directions, and to classify these type of dots. So as you see here, in neural network, once we have one separation, and then we have another line that classifies the next, and then we have this model. This is very similar to how the brain cells work and how they interact with each other. That's why it's called neural network. Actually, it's a really nice, I think, picture that shows it looks like a regression. It looks like a ninja, and it really wants to, in neural network, it cuts in any regions that can classify, but in logistic regression, it only cuts in one line. Then the next type of classification is support vector machine. So this is actually a bit deeper into the art of splitting data into two. Because if you look at these points, green and also red, you can see that there can be many lines to split these. So we do that. We just draw a yellow line and also we draw a purple line. You see, then we calculate the error and see what's the distance between each of these points with these lines. It might seem that the yellow line is too close, but also it has a risk of failing because if you move this line a bit to here, it can misclassify these two dots. So, but the purple one seems the more stable one, so it's really nicely spaced. So if you move it up and down, it really doesn't matter because it can again classify really nicely. So, and these 4 points really do not matter in this model because we just want to create a model that has the optimal margin between the closest dots to the line. In here, instead of gradient descent, we call it linear optimization. It's the same concept. They also say it's very similar to a surgeon when wants to cut a tissue. When they want to cut it, first she sees if she can really nicely classify like the two side of the tissue and then makes the cut. So this is actually support vector machine. Now, when the line is not enough, when you cannot, in here, you cannot really make a line to separate these dots from each other. So what can we do? This is one way. We can actually make a curve and to separate these from each other. Or you can move them up in a 3D dimension. And you see that there is a plane that can really separate these from each other. So which one is better? Actually, these are the same. And these are part of the kernel trick that support vector machine does. So it can look at the data in a linear way, but also it can look at the data in a polynomial way and looks and find very complex and complicated relationships as well. So again, with the surgeon example, if the surgeon wants to make a cut in here between apple and oranges, she just needs to move them up, the apples up and the oranges down, and then make a cut, like in 3D dimension. So the objective of support vector machine is to find a hyperplane that is in n-dimensional space and can classify the data points. So you can, to separate these two classes of data points, there are many possible hyperplanes that can be chosen. But how this machine does is to find a plane that has maximum margin, means a maximum distance between data points of both classes. And this maximizing the margin distance, it provides a reinforcement. So for the future data points, it can be classified with more confidence. So it will reduce the error. Because if it's too close to each of these dots, if you run the algorithm again, you might misclassify these dots to blue ones. So this is a very important concept in support vector machine to find this maximum distance. And as you see, the hyperplanes, they can be in 2 or 3 dimensions. And it can also calculate these type of relationships as well. And I think I mentioned this before. So this is a small margin and this is a very large margin. What we want is the optimal one. So we try to find the best model that fits with the maximum distance, and it doesn't create a small or large margin. What are the pros and cons? So the good thing about this model is that it creates a clear margin of separation. So that's a really good work of this model. It's really effective in high dimensional spaces and high dimensional data. And especially it's very effective if the number of dimensions is greater than number of samples. And but what are the cons? It really doesn't perform well if you have a large data. So in that case, you have to use other complex machine learning algorithms. And if the data has more noise, it really cannot perform well. And it cannot really directly provide probability estimates. So you have to do five-fold cross-validation to calculate those. So these are some of the issues with this type of model. Any questions from here?
There is actually a new one in the chat. So from Anna, if the data only has X and Y, how can you turn it into 3 dimensions to move it to separate planes?
It's actually, so the data can have X and Y, but the dimension of the data and the correlation with each other is that matters. So if there is like different categories within each feature, then that's how you can really separate it in 3 dimensions. So it's really for complex relationships, not for linear ones. If there's a linear relationship between each of the features, you just use the linear support vector machine. But if you have more complex relationships and more dimensions in your data, then you use the other like higher dimensions with the kernel trick.
Thank you. We have another question from Farzan. So in the process of adding additional dimension, for doing that, should convert the matrix to tensor, but with same extra parameters, right? Okay, I'm not sure I understand the question, Farzan. Could you reformulate in the chat? And we have another question from Melissa. What does it mean to have noise?
So for the first question, if you want to use this in different dimensions, if you want to like assess the polynomial relationships, then there is in the algorithm, there is a way that you can choose what type of algorithm you want to have. Do you want to assess a linear relationship, or do you want to assess polynomial relationships? In that way, you can choose that, and that's for more complex and data with more dimensions. And for the other question was about, sorry, what was the second question?
It's a general question. What does it mean to have noise, I guess, in the data?
Oh, so noise, there can be a lot of noise in the data. And that's why cleaning the data is really important. You have to first see how, if you have any missing data, if there are any data that any like features that correlate with each other, really highly correlate with each other, because usually machine learning algorithms can handle that. But if they're highly correlated, we just propose to reduce some type of machine learning to decrease the dimensionality of the data, and then use that. And then there are some, if you don't clean the data, there are some like some of the features that are not appropriately like labeled, or so that's why you have to see what type of data are you using. Is it like a clean data? Sometimes you cannot really clean your data. You have to use your machine learning to clean it. For example, with PCA algorithm, you just choose the high dimensionality data and run your models on that. So sometimes you have to create your model on the raw data, but this model really cannot work effectively if it's not like a clean good data, if there is any noise in it.
Thank you very much, Dr. Azizi.
Perfect. Okay, so the next very common actually model is decision tree. So for decision tree, we just give an example of Apple Store and Google Play. So our goal is to actually recommend apps to users. So we try to first gather a table of data of our current users to see how we can create a rule that can suggest apps to different age range and gender. So as you see in here, each one of these 6 people, they have recorded their gender and age and the app that they have downloaded. And so the first person is a female, 15 years old, and have downloaded Pokemon Go app. So so if we want to just eyeball this, you might say, okay, I want to divide this based on gender first. But then there is a mistake. If you do that, then you cannot really stratify after that. It wouldn't be that accurate. But then if you try to stratify based on age, you can say, okay, I will stratify based on age less than 20 and more than 20. Those who are less than 20, they mostly use Pokemon Go. And then based on gender, those who are older, usually females download WhatsApp and males download WeChat. So this is how we actually create a tree, and we can actually predict in the future based on this algorithm. So for example, if we have like a 16-year-old female, we know that it's less than 20, so it's Pokemon Go. And that's a really nice split. So this is the concept of decision trees. It will create these tree leaves, and until you can really divide your data and create a classification, and until it becomes 0. So there are some terminologies that they usually use in decision trees. One of them is, the most important one is root node. So root node is the starting node that the tree starts. It has only child nodes. And then we have internal node. So internal node is all in between root node and the leaf nodes. And at the end, the green ones are the leaf nodes. So these ones are the nodes that are at the end of the tree, and they do not have any children, and they're just completely called leaves. And then we also have parent nodes. So in any 2 connected nodes, the one that is higher hierarchy, we call it a parent node. The definition of a splitting, it means that if we divide a node into 2 or more children node, that's called the splitting. And pruning, it's so if you have a big data with a lot of features, this tree can go on like on and on till you have 0 in each of the leaves. So and that's called overfitting, because that's not a real relationship. What do we do to create a best model is we actually prune the tree. We literally cut the leaves, and we create a really nice leaf based on the criteria for our tree. We set up a criteria, and then we prune the tree to avoid overfitting and to have a really good model that can be generalizable in the future and create a similar output. So how do we create a tree from tabular data? And which features should be selected as the root node? And on what basis should a node split? So decision tree can be also be used in regression models, and also in classification models. If we have regression models, the value that is usually obtained by the leaf node in training data is mean response of observations. And if it's a categorical, if it's a classification, the value obtained by leaf nodes is the mode response. And so there are some criteria to respond these questions. How do we know when to split? So usually the decision of making a strategic split is really affects the tree accuracy. And so when you split each node, the purity of the node should increase and respect the target value after a split. So there is this index called Gini impurity or Gini index. So Gini says if we select two items from a population at a random, so they must be in the same class, and at a probability for this should be 1 if the population is pure. So it really works in categorical variable with the success and failure, and in the binary and classification. If we have higher Gini index, it means that at the end of our leaves, we should have more homogeneity. So that goes to 1. And then another way to split is based on chi-square. So this algorithm finds out the statistical significance difference between subnodes and parent nodes. And we can measure it by sum of squares of a standardized difference between observed and expected frequency of the target. And this way, you can also calculate the higher the value of chi-square, the higher the statistical significance of difference between subnode and parent node. And so that's how you decide also how much you want the node to split. Another criteria is information gain. So when you have a less impure node, it means that at the end of your leaves, your tree, you should have very similar characteristics between observations. So when the node is less impure, it requires less information. And when it's more pure, it requires more information. So usually with the information gain, they say that it's when the sample is completely homogeneous and pure, the entropy is 0. And when the entropy is 0, the information gain increases. So information gain is actually variance entropy minus 1. So your information gain increases when the entropy decreases. Another way to decide if we want our tree to split more is reduction in variance. This is actually algorithm used for continuous variables, so for regression. And we can decide a standard formula for variance to choose the best split. So we want the variance to decrease also. How do we avoid overfitting? What is overfitting? So overfitting means if we continue our model, if we run our model, we have a really big tree, it really finds some relationships that are not real in real life. So it's not really applicable in other type of data. We want to avoid this. So in order to avoid overfitting, we have to put some constraint on our model and we have to prune it. What are these constraints for decision tree? you can have a minimum sample for node split. So you say, okay, for if my sample reaches to 20, I want to stop the split. Or you can have a minimum sample for a leaf node as well. So in each leaf node, if you have less than 10, I don't want to go further. Or maximum depth of the tree also. You can decide this when you run your algorithm. Maximum number of the leaf nodes and maximum features to consider for a split. So you might have 40 features, but you really don't want to have a tree that has all those 40 features. You want to have the most important ones. So you just constrict that to, okay, I just want to see the 20 features. So that's how you can avoid overfitting and avoid finding relationships that are not real. This is literally how we avoid overfitting in decision trees is by pruning data. And there are different processes to prune data. Is really we cannot cover that in this session, but there is pre-processing pruning and also post-processing pruning. So in order to avoid overfeeding. What are the advantages and disadvantages of this type of model? So this type of model, again, is really easy to visualize and interpret, and that's why it's really common. It's very useful for data exploration. You want to find the most important features in your data and see how how you can find a rule to actually split your data to predict your outcome. That's a really good way. It really requires less data cleaning, and the type of data is not a constraint. You can have both categorical and numerical data. But there are disadvantages. So there is a lot higher chance of overfeeding in this type of model. And for continuous data, it loses some information associated with numerical variables because it classifies them into different categories. So that's one thing that also in EPI, we really don't want to do that, because if you categorize numerical data, you will lose information. So we avoid doing that. But this is one of the disadvantages of decision trees. Okay, so I think we covered on down left, you see supervised learning classification. That's what we covered today. The next most important type of classification is gradient boosting tree, and that's what I'm gonna explain next. But let's have questions about the previous one if you have any.
There was a question about the root node, and it's from Chenza. The root node would have the most noise, right? So it's again.
Yes. So you start with the most noise, and then when you go down to the leaves, you increase the purity and impurity and decrease the noise. And I have an example that I will show you that it shows how the gain index will also change by the end. But yeah, that's correct.
We have other questions. One is from Amna. In what situation would Gini give a different results from information gain?
That's a really good point. So I'm not really sure about this, if this one can be on the opposite side of each other, because they're actually on opposite, like when Gini increases, information gain decreases. So they have this like opposite side relationship with each other, if I'm not mistaken.
Maybe it's problem dependent as well.
Yeah, exactly. Yeah.
Thank you. We have another question from Umar. What does it mean exactly for a sample to be pure?
So as I mentioned, so in the beginning, Let me actually show it to you here. So in the beginning, you have most of your features like in the root node, and then you want to classify based on the features, but at the end, like the leaves, you will have only one type, so one type of feature. So that's how it's called impurity increases. Means purity increases means that there is less noise and they're very similar to each other. That's how you know that you cannot really divide after this. So when you go from up to down, it's how it works in decision tree.
Thank you very much. We have a last question for now from Amin Reza. In some cases, can we count on noise as an outlier of the data?
Yeah, that's true. One of the noises in the data is outliers, and there are multiple ways to deal with outliers. So yeah, one of the things can be also outliers as a noise.
Thank you. You have a lot of thank you in the chat. I think you can keep going for now.
Amazing. Okay, so the next part, I'm going to go over one of the most important and my favorite models is gradient boosting. So what is gradient descent? I think I mentioned this before, but let's go over that again. So gradient descent is, for example, imagine if you're on top of the mountain, you have the higher error, higher loss, and then you want to come down to the mountain, but you don't want to lose a lot. You don't want to have more loss or cost. So you want to have a model that has that reaches the best way, but with minimum loss or cost, with minimum error. So that's why it's called gradient descent. And you can also see in the model, so in this way, you see between cost and how much the model runs. You have the minimum cost for this model, so minimum error. So that's how we define it. And then we have learning rate. That is important to know before we go to gradient boosting. So when you run your model, like especially in machine learning, you might run it 1,000 times. So it really depends on your learning rate. What's the rate of each model to create? So if you create a very small learning rate, so you see your steps become very closer, you might find a very weird relationships, very unusual and like not very common relationships between features and outcome. But if you take bigger steps and you just take a really big amount of features and observations, you might also risk of not finding correct relationships. So that's a balance that you have to find, and that is called learning rate in machine learning. It shouldn't be too big, it shouldn't be too small. So how do we decide it? We usually decide it by grid search. So I will explain later how we do grid search, but grid search is a way to find the best and optimal model components. So it will run by cross-validation. It will run like 1,000 times, and it will find the best learning rate, the best other model parameters, and then you can use that best optimal model parameters in your model and create your final model. So that's how we really define this. So now what is gradient boosting? So gradient boosting, the previous models that I just told you, linear regression, logistic regression, decision trees, and support vector machines, they are only based on one single predictive model. But we can add all of these models together and create a bagging or random forest by combining multiple models into an overall ensemble. So now the predictions that are made by combining these predictions, they actually make up like this big ensemble, and with averaging, it reduces variance. So bagging and random forest are really effective when it applied to models with low bias and high variance. And also, boosting is a general algorithm for building an ensemble out of very simple models. So you have, and that's what we call shallow trees. So you have a very small and shallow trees, you add them together, you create a big tree, and but that big tree has a low variance. And what's the difference between random forest and gradient boosting machine is that random forest, they build an ensemble of deep independent trees, but GBM, the one in here, it actually creates an ensemble of shallow trees in sequence with each other. So they learn with each other from the previous one. They learn from the error that was made by the previous tree, and then they create another tree. So that's why it makes it really powerful. So this is also shown in here. You see, when you train your data set, you create the first model, and then you test it on your test set, you find errors here. And then you train it again, try it on the test set, you find more errors. And then you train it again, and you try to avoid all those previous errors and find the final best model. So that's how gradient boosting works. So in here, this is a step-by-step of gradient boosting to finding relationship. So you see in the beginning, it just draws one line because it's only one tree. But then after running multiple algorithms, at the end, it can find this relationship. But finding this exact same relationship, it has also, so in here, it also finds a relationship in after 512 trees, but then the same thing happens in 1000. So what happens between 500 and 1000 is overfitting, because you have your relationship in here. If you continue building your tree one after another, it will find a relationship that is not real. It just, it really is not generalizable if you try it on other data sets. So we have to avoid this. We have to put a stop on this in here, and there is a way to do that. Again, this is a comparison of bagging and boosting. So with bagging in random forest, it handles overfitting, it reduces variance, and it has independent classifiers. But in boosting, like gradient boosting, there is a chance of overfitting, as I showed them to you, and it reduces bias and also variance. And it has sequential classifier, as I showed in the previous slide. So what are the most common boosting algorithms? So this is like a jet in machine learning. What are the most common ones? So the first one is gradient boosting GBM, like that's the, I think, original boosting machine learning algorithm. But then after that, there has been a lot of other packages that has been built, other models based on this. It's one of the most common one is extreme gradient boosting machine, and light GBM and cat boost. So the difference between light GBM is usually for, I think this is for huge amount of data. That's the limitation. Cat boost is an algorithm that handles categorical variables in the data. And then XG boost compared to GBM. So this is one of the really most common one. It has a variety of regularization techniques to reduce overfitting. So that's a really good point compared to original GBM. And it can improve performance as well. Also, you don't really have to worry about imputing your missing values in your data set because this model can handle missing values on its own. And yeah, I think that's it. These are, I think, the most common. Also, there are some other like features of XGBoost that are mentioned here as well. Okay, so what are the steps of running a machine learning algorithm? So we learned about logistic regression. We learned about support vector machines, random forest, XGBoost. So the first step, as I mentioned before, is pre-processing your data set. So you have to clean your data set. You should find the missing data, missingness. You should find a collinearity between your features. And if you wanna categorize your, like you might have features that are really like they have 30 categories. So you have to be able to reduce that dimension. And there are a lot of ways to reduce number of features if you have a lot of them, and choose the ones that they have high dimensionality to increase your model performance. After that, you will select your ML models based on the type of outcome that you have, type of feature, number of observations, because each of these, they have their own limitations. So you will choose the ones that are the best for your outcome and your data. Then the next step is hyperparameter optimization. So what is this? This is actually what I told you about overfitting, finding relationships that are not generalizable. So in order to avoid that, we have a lot of factors in each of these models that can be adjusted, and we use grid search and using cross-validation to find the best parameters. And using those best parameters, you can run your model and find the relationship between features and outcome. So that's a very important part of your machine learning, running the algorithm. Then at the end, so one of the really most important part is to stratify your test and train data set, and you should never ever mix these two together. So in the beginning, when you clean your data, just separate your test set and don't touch it, and then run any model on your train set. Because if you merge your test set with your train set, again, you will increase the risk of bias and overfitting, because you want to, after training your model, you want to try it on your test set to assess the model accuracy and other parameters for each model, the performance. So you have to have a really different and separated test set. Okay, so XGBoost has also some parameters. I will just go through them very quickly. There are three categories of parameters in XGBoost. There are some general parameters that is for overall functioning. There is booster parameters that it's for individual booster for tree or regression at each step. And there are learning task parameters that help us to optimize the model. So the general parameters is, for example, number of threads. This is actually, you can change the number of threads in your model. And also, usually the booster default is GB3. This is but you have GB3 is for tree-based model. You can change this to GB linear, so that would be for linear models. And so this silent means that if the model is activated, is going to generate some messages, and while running, so you can silent it. Is zero means not silent, one is silent, and so you can silent all the messages while running your model. And there are some booster parameters that I have highlighted, the important ones. So eta is actually very analogous to learning rate, as I mentioned before in GBM. There are a lot of these parameters that share very similar characteristics in different models, but they have different names. So this actually makes the model more robust by shrinking the weight on each step. So the value is actually between 0.001 to 0.2. And maximum depth is actually, as you remember, I said you can decide if you want, how much you want to continue your tree to grow. So you can actually decide the maximum depth of the tree, and that would help for controlling overfeeding. It's usually the typical value is between 3 to 10. And the next one is the subsample and also column sample by tree. So in here, you can decide what is the fraction of observation to be randomly sampled for each tree. So that's a very important also factor for avoiding overfeeding. And lambda and alpha are the other two important ones that are for regularization of XGBoost. And you will decide all of these when you want to run your grid search. Then evaluation metrics. So the objective is if you want to run a linear model, or if you want to run a classification model. In here, you will decide. So for the classification model, you can have binary. That would be a logistic regression, binary classification, or you can have multi. So in multi-class, if you have, for example, 3 categories in your outcome, then you can also run XGBoost. Then evaluation metric is really important. So we have RMSE, MAE, and these are for numerical, for linear model. And we have AUC, log loss, and error, M error. These are for classifications. Okay, so what is the approach for hyperparameter tuning? And this applies for all of the other algorithms that I mentioned too. So for each of those models, you have to do parameter tuning by running a grid search. So first, what do we usually do is to choose a relatively high learning rate. So at first, we just run the model with all the default parameters. We don't add anything like a specific, just to see and to find out what's the accuracy, and if there is any, like, what's the difference between training and testing accuracy too. Then we tune the tree specific parameters, and as I mentioned in the previous slide, and then we tune the regularization parameters, and at the end we lower the learning rate. When we do a grid search, we ask the model to do it by cross-validation. So it will run, the cross-validation can be 10 times or 5 times. So it will run the model 5 times or 10 times to find the best optimal hyperparameters, and then you can use that to run your model. So this is how we understand overfitting. You see, you run your model, you run a model on training set and also on test set, and then you calculate the error. For here, we have classification error, and we also have AUC. These are the most common metrics. that we use in classification. As you see, when we reach like 100 in here and also 100 in here, that's where you see that train and test are going separate ways, and that's how you know that you are overfeeding after this. So this is a really good, I think, plot to also find out if you're overfeeding or not, and what's the number of estimator and number of trees that this happened. So this is one example of grid search and hyperparameter tuning. So you can decide how you wanna optimize your grid search. Do you wanna, which metric, which error you wanna use? So in here, I've used error and also area under curve. And then you give different examples for each of those parameters. For example, for learning rate, I wanna try 0.1, 0.01, or 0.5, or 0.05. So if you add more components in here, you will increase your runtime. And like you can run the algorithm by days. It really depends on the server you're using, your computer. So at first, I wouldn't recommend to add a lot of like examples in here. It's better to start from a small, and then based on the time that you get for running that, you can increase the number of like these different options. And at the end, it will run the model 10 times by using each of these. And it will calculate the area under curve accuracy, and it will give you the model with the highest area under curve and accuracy, so you can use those parameters in your model to calculate other features that I explained. Okay. Any questions to hear about the model? Next topic is about how we interpret machine learning. This is very common in most of the models. I'm presenting about XGBoost, but that also applies for other models as well. So if you have any questions, or if not, I can go to this one.
There was some questions, but it was about the learning rate, and Dr. Maliki answered them. So I think we can keep going for now.
Okay, amazing. So what is interpretable machine learning? Machine learning is very common to be known as a black box. So it's really hard to interpret what's inside the machine learning. It usually gives us accuracy, model metrics, you can calculate those, but it's really hard to find out what are the relationships between features and outcomes, and what are the relationships between each of the features even together. Do they interact with each other? Which one is the most important ones? So these are the I think outcome that we are really looking for. Finding model accuracy and which model is better is good, but especially in medicine, we want to see what are the relationship between each feature and outcome, and what's the direction too. If, for example, if someone so in our model, we find that hypertension, taking these type of medications, obesity is going to increase risk of cardiovascular diseases. But I want to see what's the direction of it. Sometimes it's not as obvious of having hypertension that increases cardiovascular diseases. There are some type of features that you really cannot guess the direction. So I really want to know what's the direction of each feature. There are some packages that help us with that. So the first one is feature importance. So feature importance will help you to actually find the most important features in your model based on different criteria. So one criteria is feature weight. The score is usually calculated based on the number of times that each feature appears in the trees. So that's one important. It's really based on the outcome and the problem that you have. You can decide which one is more important for you. Then feature gain is usually the score is calculated based on average gain of each split. which uses the feature, and then feature coverage is actually calculated based on average coverage of a split which uses the feature. So based on these, the model can calculate, for example, top most important features in your model. Also, you can have if your feature importance presented as a tree, as I mentioned before. The same rule applies as in decision trees. So when they're higher in the tree, they're most important. When they go down, they lose their importance. The next one is partial dependence. So partial dependence is actually my favorite, is shows the direction of each feature in the model with outcome. And it also considers the effect of other features as well. And that's one of the unique thing about machine learning. In regular stats, you can do like linear model, you can do univariable models, but it really doesn't get the effect of all the other factors. So, but in here, you can see the direction of each feature by considering the effect of other factors in the model, and that's very unique. Then there is individual conditional expectation, ICE. ICE is very similar to PDP. So in PDP, you average the predicted values across all observations and then plot that individual observation level prediction. But in here, you actually present each of the observations. So this is actually all of my data. And you see, you can see the effect of each one of them separate and also together as well. So it's really, so PDP is average of the lines of this ICE plot. You can also ask the algorithm to create this average for you too, so you can compare. But when you see that this is very scattered, but this is very like concise and together, so this is a centered ICE curve and this is a non-centered one. But usually if the relationship is really strong, it's more centered than compared to like a scattered ones. If you see that it's all over the place, it's not that strong. Okay, so these were, there are also other, I didn't add shapely values in here. These are now really common. So shapely values is very similar to feature importance, but with different values. They have created their own scores. So you can also present your feature importance using shapely values, shape values, and they also have interaction plot and dependence plot as well. So this is a very common one to present your results. Okay, so now I'm just going to go over model metrics very quickly, and then we have to go over the quotes together. So as I mentioned, you should never merge your testing and training data together. When you separate your test set, you should never run your algorithm on that till the end when you want to assess your model accuracy. So now let's see how we collect, what are the model metrics for classification and how do we calculate them? So imagine if you want to identify your outcome is if the patient is, if you have a sick person compared to a healthy person, you want to classify these two from each other. If your algorithm identifies the person as sick, like predicts as sick, and also the patient is also sick, that's a true positive. If the algorithm predicts as healthy and then the patient is diagnosed sick, is false positive. And similarly for healthy patients, if they're healthy and your algorithm just identifies them as sick, so that's false negative, and then the other way is true negative. So one of the ways to calculate model metric is to create a confusion matrix. So confusion matrix helps you to identify these true positive, false, negative, and true negatives. And with that, you can calculate out of all of these patients, how many did they classify correctly? That's accuracy. So it would be 1,000 plus 8,000 to the total. That would be the 10,000. And so it's 90% accuracy. But then for different problems and different models, there is some part that is more important for you. If you want to identify the ones that are positive, or if you want to identify those that are negative, which one is more important for you? In medical models, for us, if we have false positives, it's okay. But if we have false negative for a screening test, it's not okay. We really want to, like, it's better to overdiagnose than underdiagnose. So, but if you want to detect spams in your email, you really, if have false positive is not okay. You don't want to have your real emails go to a spam. But if you have false negatives, that's okay. If you see the spam ones in your real emails. So there are different type of models, and different things are important for you. So in here, for the patient one, so we call this a high recall model. This one is a high precision model. So precision means out of the patients that were diagnosed with an illness, how many of them were correctly? So it's 55. But for us, it's more important. And for the spam folder, same thing. How many of the spam folders were actually a spam? 76. But recall, it shows out of those that were sick, how many of them were correctly diagnosed? Now we have 83. So this is really important for me to identify the sick people. But for here, for a recall, out of those that were spam emails, how many were correctly sent to spam folders? 37. So it's had a low recall. That's okay for me, because I really don't want to miss the good emails going to spam. It's okay if I see a spam in my inbox. So in the medical model, our recall is higher, and that's how I like it. In a spam detector, the precision is higher, and how I like it. The ideal way is to have both of them high, but it's not really compatible with real life. So usually you have to choose which way is directed. We try to have a good predictive model that has high accuracy, high precision, high recall, but since it's impossible, you have to choose which way is better for your model and your outcome, and then you can present your results based on that and classify them. F1 score is actually the average of recall and precision, and that's usually also presented. So now I want to show you some examples of the most. Do you have any questions still here before I show you the examples?
I see no question. Oh, yes, there is actually one that just entered from Amna. In your research, do you think in terms of ethics only in your research, do you think in terms of ethics, only interpretable machine learning models should be used in healthcare?
That's a really good question. In healthcare, sometimes it's very rare. Like people don't like to use machine learning because of that interpretability issue. But I would say it really depends on the problem and how the machine learning is going to help. So I'm going to show you one example after showing the codes is sometimes machine learning is only to show that, okay, if I have this model with X number of features, and then I have another model with another type of features, which one is better? So it's like I use machine learning because that's the best model. It can assess the interaction between different features, and it will give me a really good accuracy and precision recall. But then I really want to see what's the how like that specific feature is associated with the disease and how I can prevent it. If I cannot really find it with machine learning, we usually go back to epi. And that's how, like, some people, there are a lot of my mentors and like colleagues, they really like to see the number, and machine learning doesn't show you the number. So the odds ratio, that's the problem with healthcare. We want to see what's the, okay, if I have, for example, hypertension, I will have 3 times more probability to get to have heart like MI. So we don't have that number in machine learning, but it can be useful in a lot of other instances. For example, I want to diagnose like that specific like a cancer inside MRI that usually you cannot see that with eyes, but machine can identify it. So that's where I use machine learning. That's the best way. So you really should see what's your problem and where you can implement the best method. Is we always say that machine learning, biostat, epi, they're all tools. You should just see how you can use these tools for your problem. You should not create a problem for those tools. So that's one thing that is usually recommended.
Thank you very much, Dr. Azizi. I just want to let you know that in theory, the workshop should end at like in about 10 minutes. So maybe it would be nice to see some application on this with the collabs you've made, because I've seen you have made a lot of work creating the collabs. So it would be cool to go through them. I don't know if that was the plan.
Yeah,
Okay.
absolutely.
Perfect.
So I just wanted to show you some examples of how do we run these models. So I start with logistic regression model. That's the easiest model that you can use. And one thing that we usually recommend is to use different models together. Sometimes if your data is like you have good amount of data, is clean, the good you have a lot of features, you can use most of these algorithms. So one thing that we would recommend is to use different types of algorithms and compare them to see which one is better, which one can really predict your outcome better. And then at the end, we present the result of that one algorithm. So we compare their accuracy, their metrics, and then choose the best one and present the result and interpret that model, a specific model. That's how we usually do it. And so one of the most common one is logistic regression. So it's for this one, I think you can have these files and try it at home. For this one, I chose the data that was publicly available in GitHub. You can download it. It's a Candy data. So here, I just want to have one very simple question is candy chocolate? So my outcome is chocolate, as you see here. And then I have different types of candy that I want to predict this outcome with. So first, I want to explore the data. We just think that this data is clean. We have done that pre-processing. And we just want to see how it looks like. So I have a few features. That's not really common. We usually have more features in our machine learning, but this is just an example. And you just see what are the 5 top observations to compare and see your data. Then in the next step, we use the packages from scikit-learn. And for this, we import logistic regression. This is the one that we use. And then the next step, as I mentioned before, was to split the data into train and test and never touch the test. You have to do it, you can define the test size. In here, I chose 20% of my data to be test. And then I want to separate my outcome in my test set and also train set. So chocolate is my outcome, and then I have my features separate. So now I have everything, all the ingredients ready to run my algorithm. Then when I run my algorithm, in here, after running the algorithm, I want to predict the results on a test set too. So when I do that, I want to create a confusion matrix as I showed you before. So in here, I can calculate model accuracy, precision, and recall. This is not a real data, so you see that my precision and recall are really high, and I have really good accuracy. This is very favorable. And then I want to have ROC curve. So ROC curve, it actually is a probability curve, and it shows the degree or measure of separability. Is one of the metrics that we also use in classification. So I also draw the area under curve, and as you see again, it's a very high area under curve, 0.95. It's not real. It's really high. So this is how we usually present. But then we should also have grid search, and also should be able to interpret. And for interpretability, we do use feature importance and PDP plots. That's what I'm going to show in the next model. You can use a similar thing in here as well. So the next model is a decision tree. In here, I use the iris data set. You can download it from here. And this is a very small data set, so it really doesn't take much time for you to run them. It only has actually 5 features, and then you just get the info. It's only have 150 observations, so it's a very small data set. It's usually not recommended to run machine algorithms on such a low number because of risk of overfitting, but this is just an example. And we want to see if the data has any missing values. Decision tree and logistic regression, they're very sensitive to missingness. So you have to decide if you want to remove your missing data, or if you want to impute them or replace them with median. There are multiple ways to actually replace the missing data. And then this is opposite of XGBoost, so we really don't do that for XGBoost because it handles it well. In here, I have multi-class. So my species are 3 categories. And as you see, this is the scatter plot. I just wanted to see how these really relate with each other. And here I have this histogram. I just want to go faster so I can show it to you. So here, when I run the model, first you have to separate again, same thing, separate your outcome, which here I'm going to predict a species from your features. And then you split your train and test set. Here I have 33% on test set. in here, I also presented the terminology that I mentioned before, and Gini index, and also information gain and how we use them. So in case you want to review later. So here, at first, I run the model in the base model, as I mentioned before. So you don't really put a lot of things in here. You use decision tree classifier and import it from scikit-learn again. And then you just measure your train and test accuracy. And this is unusually high because of the low sample size. We are overfitting. Then we want to visualize this. So the most common way to visualize a decision tree is this. You can use a lot of other, there are a lot of packages that allow you to make it like pretty, like different ways, but this is a common one. As you see, when you come down, the Gini index becomes 0 and the last leaves. So after this, after it reaches 0, you can really continue. So in here, I also present feature importance. So that's for interpretability. I want to see what are the most important features in my model. And here I have the petal length and petal weight. Same thing as logistic regression, as I showed you, I create a confusion matrix and calculate precision, recall F1 score and accuracy. And then you can try it untested as well. So I also added one reference for pruning. How do we do pruning? This is like a very big topic too. How do we do pruning? I just put a tutorial for you to just read at home. It's pre-processing and post-processing pruning. You just change different variables inside your model to be able to prune and avoid overfitting. So this was this is the code for decision tree. Let me know if you have any questions about this. And next one is XGBoost. So in here, I use the income data set. You can download it from here. And same thing, I use XGBoost from scikit-learn. And this is also a database that has really low features, but the number of observations is acceptable. It's like 32,000. So that's a good number for machine learning. So I have two versions of this. One of them was I created pipelines for categorical and numerical variables. And then because it's very common for numerical variable to standardize before adding to model, so I just removed it to make it easier, but I can also share that one with you. It was for the other workshop in June. So I just made it like labeled my categorical variables in an easy way so you can follow. For example, income, I created a 0-bound category and it's labeled as less than 50K and more than 50K, and that's my outcome. Same thing I did for other variables, other features. And you can follow this till I here. So in here, oh, actually, this is not, because I removed this, I have to remove it from here. So here we just create a matrix for features and also for our target vector. So we have to separate our target, which is income, from other features. And then you can run your model. First, you split your data to test and train. And you train your base model. Again, you don't put a lot of things in your model when you want to run your base model, just to see what is the area under curve and error by running that. And then you do model assessment on the base model. And this is, again, unusually high because it's just sample data. And then you have to, you can also use this to create a plot, as I showed you before. This is a very huge difference between test and train. That shows that your model is not really doing well. So we have to do grid search. So for the grid search, in here, I have used the hyperparameters that are really common. You can use learning rate, maximum depth, number of estimators, lambda gamma for regularization. So for other machine learning types, there are different type of parameters, so you have to be aware of that. And then I want to see what's my scoring, how I can score my model, so to see which one of these are the optimum hyperparameters. And then I want to print my best model. As you can see, this is the best model characteristic. So the subsample is 1, an estimator is 400, maximum depth 3. And then I calculate the model accuracy and confusion metrics on that best model using those hyperparameters and try it on the test set. And you see I got a really good result in here as well. Then for interpretability, in here I presented feature importance and with different ways that I mentioned, with feature weight, with gain, and with sample coverage. And you can see what are the most important ones based on each one of them. There is also another way called permutation that will remove each of those, will calculate the feature importance by removing each of the features. So that's also very common. I also created a tree, and the most important one features in the tree you can see is the relationship, education number, number of education years, and capital gain. That's it, just the overview, and you can try these at home and let me know if you have any questions. You might face a lot of errors. You can search the error, or yeah, sometimes some of these don't work. So that's the best way to learn, in my opinion.
Thank you so much,
Thank you.
Dr. Azizi. It was so complete. Like you covered the whole chain of data set, and then testing your model, and then assessing performance, and all the techniques to do like hyperparameter tuning, cross-validation. I think that was very complete. I really encourage all the participants to play around with the codes, because they are like really good resources that you can use and build on. So please do it, like go through the code, like change like parameters you could, so that you can see the effects, like really use what you have now. That's really important. And now I think we have time for some questions. So if you have some, please put them on a chat, or feel free to unmute as well to ask your question. And for now, I see a lot of thank you. This was awesome on the chat. So thank you very much, Dr. Azizi, again.
My pleasure. I'm glad
do you have something to add, Dr. Maliki?
No, it was a very comprehensive. I really appreciate the efforts Dr. Azizi put in providing the material. If there is any questions from audience, we can feel free either put it in the chat or unmute and ask.
There is actually a question from Nathaniel, which is, can you visualize the grid search?
Yes, you can print it. I did that, and it just prints all the different combinations for you. And if you don't make it in order, you have to do it yourself. So you have to get all of those and make it in order. But usually if you just put the order command, then it will create it in order. So you can just see what's the other combinations and what's the change in accuracy and other features, other like metrics.
Thank you. Is there any other questions?
Andrew, I think, raised his hand.
Hello. I was wondering what is considered a high enough sensitivity for classification model to be used like medically? Like what value would you like? How high it is you? How accurate do you have to be for your results to actually be trusted?
Okay, so that's a really good question. I want to share my the last thing that I wanted to show you to you as this response for this. See, there is not a good answer. There is no good answer for this because in medicine, there are a lot of factors that we consider. And one of the most common risk score that we use right now is Chas-Vasquez score for predicting a stroke in patients with atrial fibrillation. And you can imagine, but the area under care for this is 0.57. That's almost like random. It's nothing. It's really bad. And we still use it to be because nobody has been able to beat this and to increase this number. It's usually most of it's based on clinical factors, and that has been gone forever. Like in the last 20 years, everybody has been using this, so everyone is really reluctant to change this, but we are trying to actually improve it. This was the result of our study. We added we compared different types of machine learning algorithms to see if we can increase this. And when we added different features, like for example, what was the geographical area, what was their social different type of social determinants of health inside the model, then we saw that we could improve. So it's really, I think, great learning to see that in medicine, we have to treat the patient as a whole, like not only looking at their clinical factors, but also looking at their genetic and environmental and social factors. So we have to improve it, hopefully, in the future, but it's not going well right now with our current scores.
Thank you.
Yeah, that was really good question. In general, depends on application. Sometimes even pushing something with 90% or 95%, let's say, accuracy for a balanced situation might not be good enough because the cost is very high. If you miss one patient and that patient might die, in that case, means that from out of 100 patients, 5 patients will be actually misdiagnosed, and the cost is really high. But if, for example, the cost is not associated with some misdiagnosis is not that high, in that case, you have a range to work with. Also, the baseline is important. For example, in this case, I mean, the base is almost random. So if you do something better than the baseline, it's a step forward. So no single answer or a one answer that actually cover every situation, but case by case different.
Oops.
And also maybe we can refer to the literature in like relevant topics to see what is acceptable or not.
Yeah. Any other questions? Okay, perfect. So please join me to thanks Dr. Azizi for the great lecture. We really appreciate it. Thank you.
My pleasure. Thank you so much. Have a great day.
Thank you very much, Dr. Azizi. I just want to remind the participants that if they have not completed the form for Google, the questionnaire, please to do so. The link was on the email we sent on Friday. And also we will meet again next Wednesday for a career talk, and then next weekend for future workshops. So yes. Thank you very much, Dr. Azizi, for the workshop today. It was great.
Thank you.
We learned a lot. And
thank you.
Have a great weekend, everyone.